12 in your packet, you have a blank page. What I'd like you to do is take your geometer and draw a circle. We're going to draw a total of 3 circles down the side, so don't use the biggest one, but doesn't matter too much. Drawing a circle, we're going to define a little bit of vocabulary. On this circle, go ahead and label it center C. And I'm going to mark some points on the circle A, B, and D. I'm going to connect and make line AC, and segment CB. Now I can define a few vocabulary words that we already pretty much know about this particular circle. Who can raise their hand and tell me the name for angle ACB? Who remembers? Natalie?
No.
It's just the angle. What's the name of this angle? Jordan? It is acute, not inscribed. It's the opposite of inscribed. Yes? It's the central angle. Central angle. Reviewing that vocabulary word. That an angle that has its vertex on the center is called the central angle of the circle. And then the smaller arc AB, we call the minor arc. And normally when we've used arcs in the past, we've used them as a portion of the circle to find arc length and then area of a sector. We're actually going to talk about arcs by themselves now, so we need to be able to label the rest of the circle. So if I have this one as arc AB, I need to be able to go the other way around the circle and call that arc ADB. I had to have that other point on the circle so I knew that I was talking about that part of it. And we call that the major arc. Now, just like we've already known before, the measure of angle ACB is equal to what? The measure of angle of ACB, the central angle, Jamie, is equal to the measure of arc AB. Yes, the measure of the central angle is equal to its intercepted arc. Because we judge both of them by degrees. They're both a portion of the circle. And now, how could I express then the measure of the major arc? What's the whole circle? No, the whole circle is 360. So if I knew that if I had, for example, the measure of arc AB, what could I do with that to find the measure of the major arc? Yes, Jordan? Subtract it from 360. Good. So we could say that the major arc is 360 minus the minor arc. They add up to 360. Okay, when you get a chance, draw another circle with your geometer. Label the center and a line that goes to the center. And who can tell me what that line's special name is? Haley? It is the diameter. Thank you. AB is a diameter. We already knew that. What if I wanted now to describe arc AB? That's a good question.
They're both 180.
Exactly. They're both the same. Well, I didn't do a very good job highlighting that one. They're both the same, and they're both 180. Arc AB is a semicircle. Doesn't matter which way you go around. And the measure of arc AB is going to be half of the circle, and half of 360 is 180. So the measure of a semicircle is 180. Nice. So if you know you have an arc that's defined by a diameter, you know its measure is 180. Now what happens if I were to change our diagram a bit. And I'm going to draw an angle. Oops. And I'll call that C. Who could tell me what the measure of angle ACB is? Sammy. 90. How'd you get 90 so fast? Yes, ACB is an inscribed angle. We learned inscribed angles in Chapter 9. And we know that an inscribed angle is half its intercepted arc. Well, if the intercepted arc is defined by a diameter, and that means that its intercepted arc is a semicircle, and the semicircle has a measure of 180, then half of 180 means that this is going to be a right angle. You'll see you'll see problems like that a lot, where they'll have an inscribed angle that opens up to a diameter. You just need to know that that is a 90-degree angle. Yes?
Sorry, inscribed angle equals 1/2 arc?
Yes. Yes, we learned that in Chapter 9. Now I'm just extending that to, if you're just given that, for example, an inscribed angle opens up to a diameter. All right, let's go ahead and look at page 13. And we have some pretty straightforward relationships between central angles and arcs. For example, if you know that two central angles are equal, you know that their intercepted arcs are equal. So I could say that arc PQ is congruent to arc SR. And if in the same circle I have that two arcs are congruent, what do you think I could say about their inscribed angles? Lily? Yeah, their central angles, rather, are congruent. Their inscribed angles will also be congruent. So angle QOP would be congruent to angle ROS. Now, we can also make those same judgments about a chord. This chord PS has the same endpoints as the arc that would go along with that central angle. Now, the chord is not congruent to the angle, but if you have if the two central angles are equal, their intercepted chords will also be congruent to each other, meaning chord PS is going to be congruent to chord QR. Now, this is different. We're not saying that the measure of the chord is the same as the angle. First off, we judge chords differently than we judge angles, right? Angles are measured with degrees. Chords could be in some sort of linear measurement, like centimeters or millimeters, something like that. The chords are congruent to each other if the angle is equal, which makes sense, right? If you have within a triangle two angles, right? Well, first off, the radii are congruent, right? And the angles are congruent, so the triangles are congruent, correct? Why would those two triangles be congruent? Jordan? Exactly. The triangles are equal because of SAS, therefore those chords are equal by CP/CTC. But from now on, rather than having to go through that baby proof, you know that if the central angles are equal, then their intercepted chords are congruent. So same thing here. If I have that the chords are equal, then we can think backwards. The converse is true, that the angles are equal. Angle POS is congruent to angle QOR. And lastly, if you have two arcs with the same measure, then the intercepted chords would also be congruent. And if you have two chords that are congruent, then the arcs are congruent. And the angles are congruent. They all lead to each other. So what we're going to do is that we're going to make one rule. That within the same or congruent circles, if you have congruent central angles, so central angles congruent, that will lead to arcs congruent. But arcs congruent could also lead to central angles congruent, so I'm just going to draw an arrow that way too. And if you have arcs congruent, that leads to chords congruent. But if you have chords congruent, it leads to arcs congruent. Chords also leads to angles. All three of these are interchangeable. Central angles goes to chords, chords goes to central angles. Yes. All right, turn the page. Let's look at page 15. I'd like you to draw a circle under number 1. So figure. And number 1 says, what is the measure of an arc intercepted by the side of a regular octagon? And the octagon is inscribed in the circle. So we need to draw an octagon in the circle. And the easiest way to do this is to draw the vertices first. So I started off by drawing 2 dots on the opposite sides of the circle. And then I'm going to do 2 dots on the sides there. So now I have the circle in fourths. Now I'm going to take each section and divide that in half. I have 8 dots. Connect the 8 dots and you have an octagon, more or less. It's because you started with a circle. If you ever want to draw a good octagon, start with a circle and you'll be good. And it wants to know the measure of the arc intercepted by one side. So draw the center of the circle, and it kind of helps to draw some lines from the center. So we're trying to go for this arc. Well, that arc is congruent to this angle. So if you imagined triangles whose sides go from the center to each vertice, how many triangles would you have? 8. Alright, now think about this. If I want to measure from here all the way around, how many degrees did I just do? 360. So that means each of those angles, I'm going to divide that by 8. I could get then that angle in those triangles. So 360 over 8, divide. I'll tell you, it's 45. So I know that now that this angle is 45. Well, if the central angles are 45, we know that arcs have the same measure of their central angle. So you could say then that the measure of the arc is equal to 45 degrees. Okay. Now, number 2, we have our only proof. Are there questions?
Yeah.
All right. So we're given that AC and BD, arc AC is congruent to arc BD. So let's write our given. That was easy. And we're trying to prove that chord AB and chord CD are congruent. So who could tell me the arc that chord AB intercepts? The arc that chord AB intercepts. Sammy. So I'll draw it out for you. I'm going to do it in pink. So AB would intercept chord AB. Does that make sense? Well, we'll get there. Now, chord CD would intercept arc CD. I have a lot of color now on my diagram. I'll start again then.
Why couldn't you do like...
Hold on. So here's my arc, my chord AB. It intercepts arc AB. Yes, Natalie?
Could you do it the other way?
You could, but it wouldn't be helpful. Well, it doesn't really matter. It's just, I think, less letters to write if you do it this way. And chord CD intercepts arc CD. All right. What do they have in common?
CB.
Yeah, they have CB in common from here to here. So before, you guys, when we had a line, And perhaps we knew that these parts were equal. And I asked you to prove that this was congruent to this. What property would you have used? Addition. Well, you can add arcs as well. So now I can say that arc AB is congruent to arc CD. All I did was I added arc CB. So that's just addition property. All we did was we added the same arc to congruent arcs. Alright, well today we learned that if arcs are congruent, then their intercepting or chords are congruent as well, which is what we're trying to prove. So your last step then is to say that AB is congruent to CD. All that changed then was the line went from a curvy line to a straight line. And it's really easy to do your definition. You could just say arcs congruent implies chords congruent. That's it. Easy squeezy. Let's do one more problem together. Turn the page.
Is there a special assembly?
No. Find the length of an arc that's 2/3 of a circle, and the circle has a radius of 12. So we've done arc length before. This is not new. I'll just write down the formula. Arc length is normally the measure of the arc out of 360, the portion of the circle, times 2 pi r, or pi times diameter. If you have trouble memorizing the formulas, I'd write them down. Now, this problem didn't tell me the measure of the arc, but it just told us the portion of the circle. Meaning we don't know what the arc is, although we could figure it out. But it out of 360 is 2/3 of the circle. So that means 2/3 times our 2 pi r will give us the arc length in this case. We did not need to know the measure of the arc because it already told us that it was 2/3 of the circle. So if you take 2/3 and multiply that times 2 times pi, our radius is 12, and simplify, you'll have our answer. So that's really 2/3 times 2 times 12 is 24. Cancel. And we get that the arc length is 16 pi. All right.